All right, let's do a quick blind, easy one. We got search insert position. Given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. Um, and then you must write an algorithm with ON runtime complexity. Okay, that's pretty straightforward. Um, I think I would just do like some, it's sorted. Just do like a binary search, right? Right? Yeah, I mean, yeah, it's just a binary search. Okay. um, yeah. Am I crazy? So this will be a good test to see if I remember how to do a binary search, at least quickly. Of course, I'll get there eventually. But let's see. So binary search, just to talk through it out loud, might as well. Otherwise, why am I recording this? Um, you have a lower bound and upper bound. You basically pick the medium, the being the indices. It's like if you were, my favorite analogy is like if you're looking for a page in a book, you kind of do a binary search, a pseudo binary search, just like without even thinking. Like open up the book at page 1 if you're looking for page 365. Maybe you just open up a big chunk, and then if the page number is lower than 360, you go a big chunk forward, and then if it's still lower, you go a big chunk forward, and if you go a smaller chunk every time as you get more and more precise. And then yeah, because it's sorted, we have the pleasure of just not really we don't have to think. We can just we can lop off half of the array every time. We really don't have to check every value. We might get lucky, it might be in the dead center. But basically we're taking the best possible guess every time so that if we're wrong, we'll be able to eliminate as many possibilities as we can. Another great analogy would be like Guess Who. In Guess Who, your strategy is probably you want to guess something that would eliminate as many possible candidates as you can. So so you want to choose something that eliminates about half of them. Same goes with this. So lower bound and upper bound indices. Pick middle, I guess it's median value. Yeah, no, it's the middle value because it's indices. The median would be, well, I guess it is the median. Um, Pick median. Check if target. And if not, update lower bound if target too low, upper bound if target too high. And then if lower and upper ever cross, stop. All right, cool. Makes sense. Yeah, I don't think that there's. I think that most of these search algorithms, especially at a scale of this, are going to be pretty indistinguishable. And I don't know, I'm kind of enjoying not looking anything up, and I forget how to do like a merge sort by hand. You know what I mean? So, I mean, I know the idea of it, but coding it will be a different challenge. But okay, sounds good. So lower bound, I would say lower index. So lower index equals 0, and upper index equals length of nums minus 1. Okay, so this is your initially this is just the starting bounds. Okay, and now we're going to loop through until we find it. And we can use a while loop, and the condition would be that the bounds haven't crossed over. Because basically, let me see, I think I can actually like draw this out. If we have like 1, 2, 2, 3, 4, 6, 7, 8, 9. No, actually that's a bad example because we just start. Okay, let's say we're looking for 7, but there is no 7. Well, we start, we have the lower bounds at 1 and 9, or we have the lower bound set to 1 and the upper bound set to 9, or at least the indices of where those are. We find the middle index between those two bounds. So that would actually just be a splice. We would probably use like a floor division just to pick one or the other. But we get either 4 or 5. Let's say we use floor division, so it chops down to 4. Okay? And 4 is less than 7. That means that the new lower bound would be 5, and the upper bound stays the same at 9. Now we divide those in half. Floor division, we get 6. So neither of those are true. Wait, so do you want to... I'm curious. I forget if you update the lower bound to be 1 greater than it was. So 0 and 9. Actually, it would be 0 plus 1. 8 would be 8. Because there's no 7 there. So it would be 0 plus 8 divided by 2 is 4. Right, 0, 2, 3. 0, 1, 2, 3, 4, 5, 6, 7. That always makes me feel dumb. Okay, sorry. It'd be 3.5. 3.5 gets floor divided to 4. 4 is not our target, and it's less than the target. So that means that 4 is our new bound, and 9 stays the same. 3 plus 7 divided by 2 is 5. So it'd be 0, 1, 2, 3, 4, 5. Zero, 1, 3, 1, 2, 3, 4, 5, 6. 6 is not our target, and it's lower than the upper bound. Well, it's lower than the target. So this becomes our new lower bound. I think so. The only thing I got confused about there was I was forgetting. Since we know that 6 isn't that, do we want to just skip over it? But I realized that if 6 is actually just like if the value isn't there, by going up 1 with our lower bound, we might skip over where the possible target would be. Okay. Anyway, skip. Okay, so it's lower. The lower bound is now 6, and the upper bound is now 9. So we'd say 5 plus 7 is 13. 13, 6.5 divided by 2 and give us 6. 6 would be 8. And then 8 would be higher than the target value. So it would be, yeah, it'd be higher than the target value. So 8 would be the new upper bound. I'm just trying to remember where the stopping point is. I know it's like when the upper bound and lower bound like start to cross, but I forget how we would make the target. Find the new index for the target, I mean. Because this will definitely, right now, will work for when we find it. But so this would be 5 plus 6. 5 plus 6 divided by 2 is 5 plus 5. We get the same. We go back to 6. I forget what the kill condition is. Maybe I can like cheese it by saying like, okay, well, if we get to that point where they're separated, check if neither one is the right one. And then if neither one's the right one, then we return the lower bound plus 1. I think there's a faster way of doing it. I'm totally forgetting, but let's just code it out. I'm done. Okay. While lower index is less than upper index, ooh, how can we say like while lower index is lower than upper index minus 1, and then when we get out of this, exit, that means it's got to be but I think we do have to check because there is a possible way that it could just be the upper bound. If nums equal, well, if nums lower index equals target, return lower index. I'm kind of working backwards here, but hope I'm making sense. I think it's just that added condition of you had to find where it would be. Oh, actually, you know what? We can get kind of cheesy because if we're not in this loop, unless, how big does the list have to be? Do we have to consider if it's like a list size of 1? Yes we do. Yes we do. I feel like there's one edge case that I'm not considering here. I think it's just when it's a number's length of 1. But you know, let's just write out like the actual code, and then we'll worry about the edge case later, because maybe it'll get caught. Who knows? Okay, while lower index is less than or equal to upper index minus 1 if middle equal, well, yes, a middle equals upper index minus lower index divided by floor divided by 2. If num's middle equals target return middle. If num's middle is greater than lower index equals middle, else upper index equals middle. Okay, that should work for most of them. It's just the pesky edge case. Yeah. Okay, so we could just put an edge case here if it were given a list length of 1. Because down here we could just get rid of this because this will only be reached when they are 1 apart. Which means it either has to be the lower index, the upper index, or the lower index plus 1. No, it could be the upper index plus 1, right? No, it never would. Unless we're given a list length of 2. Yeah, okay. I feel like I'm being stupid here, but I don't think it'll make that much of a difference. Num's upper index, if it's less than the target, we can just say return upper index plus 1. No, if it's less than... Just gonna do a checkup here, just an edge case. I guess I should. Okay, I guess it could be less than or equal to target, because if it's not in there, you'd still return 0, and otherwise you'd return 1. Okay. Oh, this is getting ugly. I apologize. I try to write cleaner code. Fuck it, let's just run it. Oh gosh, I'm sorry, I didn't mean to swear. Time limit exceeded. I feel really silly because this is code I've seen like 1,000 times over. I'm not doing it right. That's embarrassing. I guess it's all a learning experience. Okay. So we're reassigning the index. Let's just do my little trick of printing out the indices as we work. Ooh, so it never actually changes them. Okay. It does the same thing over and over again. It's 1, 3. Again and again. Why is that the case? Oh, maybe we had to actually do middle plus 1. Let's see if that works. Wrong answer. Okay. I'm totally forgetting how to do this. I'm gonna call this